and also the qualification of components for aerospace applications. I would be touching upon a few metal additive manufacturing case studies. And also I would be talking about the opportunities, future trends, and concluding my talk after that. So you all may be familiar with additive manufacturing since already I think some talks have happened in this area. So anyway, for the sake of completeness, I would be touching upon this. So additive manufacturing is defined as the process of joining materials to make objects from 3D model data and usually layer upon layer as opposed to subtractive manufacturing methodologies. So this is the classical definition given by ASTM F42 Committee for Additive Manufacturing. And also, you would have heard about several synonyms about additive manufacturing, which is nothing but 3D printing, rapid prototyping, direct digital manufacturing, layered manufacturing, and additive fabrication. So here we are trying to add material to create an object rather than removing material from the stock in almost all the conventional manufacturing process. And we are moving from design for manufacturing to manufacturing for design. So I'll be talking about when I come to the design aspects of it. And we also have very good design flexibility, and we can easily try out newer and newer ideas. So the starting point for additive manufacturing is the CAD software, wherein we have the 3D model of the part that needs to be made. And once we have the 3D model of the part from the CAD software, we can get the .htl file, which is nothing but the input that is fed into the CAM software. And the CAM software generates the toolpath commands or the slicing data that is required to make the 3D printed part. And after that, using the 3D printer and the material as a feedstock, with this as the input, with the toolpath, the command file as the input, we can 3D print the part layer upon layer. And once it is subjected to complete quality control and inspection, we can induct the part into the program. So coming to the metal additive manufacturing technologies, these can be broadly classified under powder bed fusion technology, directed energy deposition technology, and solid state fusion technologies. So under powder bed fusion, we have powder as a feedstock, and we can have either laser or electron beam as a heat source to melt the material. And under directed energy deposition, we can have either powder or wire as a feedstock. So here again, we have laser as a heat source. And for wire DED process, we can have electron beam wire DED, or we can have laser wire DED process or arc wire DED process. And coming to solid state fusion technique, we can use either foil as a feedstock in case of ultrasonic additive manufacturing. We can use rods as a feedstock in case of additive friction stir processing. And we can use powder as a feedstock in case of cold spray deposition. So as the name suggests, we do not have any melting involved, only additive manufacturing happens in the solid state. So yeah, these are the various schematic of a laser powder bed fusion, electron beam powder bed fusion, and laser DED process. You can see here, in case of powder bed fusion, all the process happens on the bed, whereas in case of in case of directed energy deposition process, it is happening in the form of powder spray, and also there's a coaxial laser beam coming and melting these powders that is being sprayed, and that melts and deposits onto the substrate. So we don't have a powder bed in case of, I mean, similar to, unlike the powder bed fusion process. And in case of wire DED process, you have wire as a feedstock, and you can have either electron beam or laser or arc as the heating source. So coming to the capabilities of additive manufacturing process, we can manufacture parts or structures that are normally impossible or difficult to manufacture through conventional manufacturing process. And parts with intricate internal structures or complex shapes can easily be manufactured. And we can also replace we can replace an entire multi-part assembly with a single AM part. So I'll touch upon on one of my case studies. And also we can manufacture parts on demand without the need for an entire factory. In case of a conventional manufacturing process such as forging or casting, we need an entire factory to manufacture a single part. So unlike that, we can manufacture parts on demand without the need for an entire factory setup. And we can also look at the production of novel materials with unique physical and mechanical properties. And also additive manufacturing gives us one unique advantage. We can repair the components and we can also add new functionality onto the existing parts. So coming to the motivation for additive manufacturing for space applications, you can see here the cost of injecting a payload into space can vary anywhere between $5,000 to $20,000 per kilogram. So that is the cost required to place 1 kilogram of an object into space. So any weight saved by way of additive manufacturing, by optimizing the designs, we can save the weight, we can reduce the part count, which can directly translate into these kinds of cost savings. So ultimately, we are looking at making parts that are cost effective, lighter, and more reliable in a short turnaround time. And we can also make advanced alloys with exotic physical and mechanical properties. We can also have combinations of alloys in our space applications. We have different requirements wherein you'll require bimetallic joints, multi-material components, and also functionally graded materials. All these kinds of different combinations of materials or alloys can be definitely be made through additive manufacturing. And also for academicians, there's a tremendous scope for R&D, and there's tremendous challenge for metallurgists to develop materials for hostile environments, be it in form of extreme temperatures, right from cryogenic temperature, ambient temperature, and elevated temperature. And also, we require excellent oxidation resistance, corrosion resistance, and embrittlement resistance. And coming to loads, we can have static and dynamic loads, or there can be applications which require very high pressures. And of course, since we are talking about systems for space applications, we are looking at minimal design margins. So these are the challenges that exist, and these are the main motivation factors for using additive manufacturing for space applications. So coming to the major process steps in the iterative cycle for additive manufacturing of aerospace components, you can see here, it starts with design and pre-processing, wherein we are looking at part design. We can analyze the component that is to be made through additive manufacturing. And also we need to generate some supports in case of powder bed fusion process. And since we are using 3D model as the input data, we need to slice the model, or in case of directed energy deposition process, we need to generate the tool path for depositing that component layer upon layer. And of course, we need to have process parameter optimization for carrying out the AT manufacturing process itself, wherein we'll use, I'll mainly focus my area on metal additive manufacturing. So we'll be using metal as feedstock, either in the form of powders or wires. And after the additive manufacturing process is completed, the part needs to be subjected to post-processing. So it involves powder removal, heat treatment to achieve the required mechanical properties, support removal, and also build plate removal. And also we need to subject the component to inspection. And in some cases, to achieve the dimensional tolerance requirements as per the drawings, we need to carry out machining. Sometimes we need to carry out welding, polishing, and also cleaning of the parts. And once the part has been put into service, there also we need to monitor what are the assembly requirements, and also we need to see how the metallurgy or the mechanical properties of the part that has been made through additive manufacturing uh, behaves. And also we need to look into the part production plan once we complete all these aspects. So in all these stages, we have qualification involved at each and every stage before inducting the part into our program. So this slide shows a glimpse of metal additive manufacturing for space applications. It gives a world scenario. So we were early adopters of additive manufacturing at ISRO way back in 2017, wherein this Northwest Feed Cluster Assembly of GSAT-19 satellite was made through additive manufacturing. Of course, it was a satellite part, not a launch vehicle structural application part. And you would have seen SpaceX has widely adopted additive manufacturing into their supply chain. The Super Draco engine made by SpaceX and also Merlin engine main oxidizer valve have been made through additive manufacturing route. And also we have seen ESA has extensively used additive manufacturing, especially in development of Ariane 6 launch vehicle. So this is one example of a propulsion system module wherein more than 240 elements have been 3D printed as a single component. So earlier, each of these injector elements they used to make separately by machining route and then braze onto a base plate to realize this particular component. So now they are able to 3D print this as a single component. And you would have also seen relativity space using additive manufacturing extensively for making the propellant tanks as shown here. And our own startups, both Skyroot and Agnikul, have been using 3D printing for manufacturing their engines, both the cryogenic engine from Skyroot as well as the semi-cryogenic engine from Agnikul. And also, you can see here Rutherford engine from Rocket Lab, aerospike nozzle from Fraunhofer Institute, and also engine chamber from Cellcore have all been made through additive manufacturing. Because of the complexity involved, additive manufacturing is only manufacturing process by which these complex engines can be made. You cannot think of any other manufacturing process to make such very complex engines. So this slide again talks about different process and how different parts have already been inducted by various space agencies. So you have relativity space, which has been using additive manufacturing for manufacturing the propellant tank. Rolls-Royce has been using additive manufacturing to manufacture various engine parts. And a lot of aircraft brackets with bionic designs have also been made through additive manufacturing. And this is one example of part consolidation wherein GE has been using additive manufacturing to consolidate more than 20 parts into a single component. And this is one classic example how additive manufacturing can give us advantage of weight savings. So this is Raptor 1 engine, and you can see Raptor 3 engine, which has been made completely through additive manufacturing route. So many parts have been consolidated, and even the engine has been simplified, as you can see here in this. So this has given them a specific advantage of very high strength to thrust ratios. And also, you can see a lot of engines have been made by NASA, and it has been functionally tested before inducting into their program. So yeah, this is one example of a LEAP engine fuel injection nozzle wherein more than 20 components has been 3D printed as a single component, and it has given a weight reduction of around 30% and also resulted in better performance. On the right, you can see one particular component for our control manifolds. This is our own application, wherein conventional component used to be made by machining route and it used to weigh around 21 kilograms. So we have adopted a design for additive manufacturing approach for redesigning this component, and we could save at least 30% weight. So the defamed component and made by additive manufacturing can see is weighing only 15 kilograms. So what do you mean by design for additive manufacturing? So you have an existing design, you carry out a topology optimization. So by topology optimization, what I mean is wherever material is not required from functional point of view, we can eliminate that or remove that. So we do a topology optimization. So based on that, we do a redesign, and we subject the part, redesigned part to again analysis using ANSYS. And once we find that the redesigned part can meet the intended functional requirements, we can manufacture it using additive manufacturing. So this is one example of ESA satellite Sentinel-1 bracket made through additive manufacturing, wherein you can see 43% weight savings could be achieved compared to the conventional manufacturing process, uh, which used to manufacture the bracket in this manner. So coming to the design aspects in metal additive manufacturing, first one is design for additive manufacturing, wherein you can have optimized geometries and you can have part consolidation, you can have lattice structures for optimizing the weight, and also you can optimize, you can carry out topology optimization to reduce the weight. So coming to the design aspects in AM process selection, of course, you need to look at various process capabilities. You can look at a combination of additive manufacturing process to realize a particular part. And of course, you need to look at what is the part size and the features that are there in the part before choosing a particular process. And also you need to look at the complexities of geometries. You also need to look at the post-processing requirements in the form of machining and surface finish requirements based on the drawings that are there for different systems. We also need to take care of the thermal management. Process parameters play a key role. And also the scan strategies and support structures, they play a key role in thermal management, because when you do the 3D printing process, so it can lead to a lot of thermal stresses to be built in during the process of printing. So which can lead to, which can translate into a lot of residual stresses, which can even lead to cracking. So you need to have effective thermal management both during printing as well as during post-processing. And of course, when you talk about material selection, alloy design, heat treatment, and combinations of hot isostatic pressing and heat treatment can vary the mechanical properties. You can tailor the mechanical properties by adopting different combinations of these processes. Yeah, coming to the metal additive manufacturing process for space applications, we already discussed about powder bed fusion. So you can have electron beam or laser as a heat source. And under directed energy deposition, you can have powder or wire as a feedstock. And you can use either laser or electron beam or plasma as a heat source for melting and depositing. And of course, under solid state fusion process, cold spray process is one which has been gaining more popularity for aerospace applications. So again, we can classify these processes based on the size of the components that can be made. So powder bed fusion process are essentially classified as small format based on the size of the components that can be made. And DED process and solid state fusion process have been classified as large format process, mainly because of the size of the components that can be made. So coming to the process selection for aerospace applications, we need to look at all these aspects. We need to see what is the alloy in which that component needs to be manufactured. We need to look at the overall part size, the part complexity, feature resolution, and whether the feedstock in the form of powder or wire is available. Once the feedstock is available, we need to look at the process parameters. And also depending on the functional requirement, whether it's a single or multi-alloy component, we also need to look at the process economics and also the process availability. Most importantly, we need to look at industrial maturity of the technology and also the post-processing aspects, either in the form of heat treatment or machining to achieve the required dimensional and surface finish requirements. And we need to have a detailed characterization of the metallurgical properties of the parts that are being made through additive manufacturing. So these are the three main aspects based on which we can select or choose a process for making a component for aerospace applications. So anything which meets the technology readiness level of 6 or above, we can adopt that process for making the part for aerospace applications. By TRL 6, what I mean is the part should have been made through additive manufacturing process, should have been qualified in that particular service conditions or in the service environment. On the right, you can see the capabilities of various additive manufacturing process. So it is talking about build height versus the build diameter. So you can see laser powder bed fusion process can mainly make parts up to 1 meter class. And when you need to make components up to 4 meter class, you are essentially looking at arc wire DED process. So these are the almost all the DED process can make very large size components, and powder bed fusion mainly focuses on making smaller size components. So coming to the comparison of different metal additive manufacturing process that I talked about till now, you can see here when you're looking at a very high complexity of the part, very good accuracy and surface finish requirements, laser powder bed fusion is a process. Of course, the size is a limitation here. And when you talk about very large build volume and very large build rates and also very good mechanical properties in as deposited condition and very high material utilization and cost savings, you are looking at wire arc additive manufacturing process. And other processes such as EV powder bed fusion process and laser metal deposition process or laser DED process fall in between these two extremes. So again, you can see here when the electron beam powder bed fusion is compared with the laser powder bed fusion process, you need to compromise a little on the complexity, accuracy, and the surface finish requirements. So why we need to choose different metal additive manufacturing for space applications? So this slide, it gives a relation between the resolution and part complexity versus the part size. So here you can see when your resolution of the part or geometry of the part is very complex, you are essentially looking at powder bed fusion process. And when you're looking at low resolution or simpler geometries, you're looking at large uh, uh, format additive manufacturing process such as powder DED and wire DED process. So you can see here, again, the cost is dependent on the size of the components that can be made. So the DED process are very cost effective compared to the powder bed fusion process. And again, in India, we have so many laser powder bed fusion machines available, but there are very few lab scale machines, especially in the DED area. So this slide again talks about the feature resolution versus the deposition rate of various metal additive manufacturing process. So as I already mentioned, since we are looking at very fine feature size and laser powder bed fusion is a process, the deposition rates for making the component are very low in this. And when you look at DED process, you are looking at very high deposition rates, but you need to compromise on the feature resolution. So again, on the right, you can see when the part size is increasing, you require more material for making the part itself. So thereby the build cost increases. But when your deposition rates are increasing, your build cost decreases. But at the same time, since almost all these processes are compromising on the feature resolutions, you need to carry out post-processing in the form of machining, which again increases the cost. So it is essentially a trade-off between the deposition rate and the post-processing requirements in a large format DED process, which you need to consider before choosing a particular process. So here again, it gives a relation. This slide gives the relation between the build deposition rate and the feature resolution. So when you're looking at very fine feature resolution, powder bed fusion process are the ones wherein the build deposition rates are quite low. And almost all the DED process, the build deposition rates is quite high. And one important thing to keep in mind here is as the deposition rates are increasing, you can see here the feedstock size is increasing with the exception of cold spray process, which is again using powder as a feedstock. The powder size in case of cold spray is again 10 to 45 microns, which is similar to laser powder bed fusion. Only because there is no fusion of the powders involved, you are able to achieve very high build deposition rates. Whereas in all other processes, there is fusion of material involved except for additive friction stir deposition. So when you look at the different additive manufacturing process as listed previously, these are the photographs of the as-built components through various additive manufacturing process. So on the first image, you can see it is made through arc wire DED process. So you can see here the surface finish is very wavy. And on the right, you can see the part that has been made through laser powder bed fusion. So the surface finish is very good. And on the bottom, you can see both laser powder DED process and laser wire DED process. These are better compared to wire arc additive manufacturing process, but inferior compared to the laser powder bed fusion process. So essentially, all these three process routes, you need to carry out machining before the part can be injected into your program. So now we'll move into the quality control aspects for metal additive manufacturing process for space applications. So why you need to look at quality control? Because we are talking about space applications wherein very high costs are involved. So reliability plays a very key role. So reliability of the parts that are being made through additive manufacturing also need to be established. And also, there are very few established standards for qualification and certification as on date. And also, we are looking at complex combinations of various machines, materials, and process. And since it's a relatively newer process, there's absence of reliable database available, which reduces the level of confidence to adopt additive manufacturing process into our supply chain. And also, we need to look at potential issues in AM parts with respect to the build process parameters used. And since we are making wide varieties of additive manufacturing parts, we need to look at qualification of family of parts rather than individual components. And non-destructive testing of additive manufactured parts also plays an important role in quality control of components made for space applications. So when you look at the available standards which are there for as reference for metal additive manufacturing, you can see here there are a lot of standards from AMS and ASTM. Of course, 4 to 5 years back, these standards were limited. Now we have more standards coming out from ASTM and AMS. And also you have ASTM AMS standards for various powders that are used as feedstock. We have ASTM and AMS standards for mechanical properties of various alloys. We have AMS standards available for heat treatment cycles. Of course, this is not for additive manufacturing. These are for wrought alloys. So we can use these as guidelines, and we have to devise our own heat treatment cycles for additive manufactured parts. And of course, since a lot of OEMs are making these powders and wires, they publish their data sheets. So there are OEM data sheets available for various additive manufactured alloys. And there's one comprehensive standard from AWS, from American Welding Society, that is AWS D20.1, for both additive manufacturing of components as well as NDT of AM components. So this standard evolved in 2019, and
ஆமாங்க நைட் ஆனா வராது.
based on all these standards, we have been devising our own standards for qualifying our components. We are generating a lot of data, and we are also looking at establishing the NDT capabilities for various parts that are being made through additive manufacturing. So this slide again gives a glimpse of various materials and heat treatment conditions and the properties in different orientations. These are the different ASTM standards that are available. I thought I'll show as an example of what different ASTM standards talk about different AM materials and the heat treatment conditions and the mechanical properties that are listed here. So now we'll move into the qualification methodology that we are adopting for additively manufactured components. So when we talk about qualification, we need to look at the qualification right from the raw material stage. So the raw material I have taken here as an example of powder. So we need to look at what are the powder stage qualification activities that we need to do. So coming to the powders, we need to look at the chemical composition, the shape of the powder. So mostly for additive manufacturing, we use spherical shape powders. And also we need to look at the average particle size and distribution. We need to look at the flowability of the powders. When we talk about the process, we'll know the importance of this. And also we need to look at the apparent density, tap density, and the Hausner ratio, which is nothing but a ratio of tap density to apparent density. So we need to ensure that the powder meets all these specification requirements before using it for 3D printing of the components. And next we move on to the equipment qualification. So by equipment, we mean the machine that is being used to 3D print, the heat treatment furnace that is used to heat treat the components, and also the CNC machine, the measurement tools, the CMM used for inspection, and also the sieves used for sieving of powders. After this, we go into the first article inspection stage. So here, as a part of this, we are qualifying the machine, we are qualifying the material that is being used as a feedstock, and also we are qualifying the process parameters. So here what we do is we print an exclusive build consisting of cubes, test coupons for carrying out the tensile properties, and also we 3D print the hardware which is called as the first article. We also check the density, microstructure, and the hardness using those cubes that are printed along with this hardware. And we also check the physical properties. We need to carry out non-destructive testing either by way of radiography testing or dye penetrant testing or computer tomography. We need to evaluate the mechanical properties. And very often we tend to replace castings with additively manufactured parts. So we need to do cut-up tests similar to what we do in case of castings. And after this hardware has been made, we subject it to functional testing as well. By functional testing, what I mean is we need to test that particular part in the actual service conditions or in the service environment. So once this part meets all these requirements, we can say that we have successfully completed the first article inspection stage, and thereafter we can move into the production hardware stage. So here again, along with the hardware, we print some coupons. Of course, we don't print so many coupons as in case of first article inspection stage. So we have reduced number of samples. Of course, we need to carry out NDT of both the hardware as well as the samples. And we can do cut-up test and functional test on random hardware to ensure that your process that has been adopted to make these components is in control. And of course, the last step is the post-processing. It can be in the form of stress relieving or heat treatment to achieve the required mechanical properties, short blasting to achieve the required surface finish, and also surface treatment to achieve the required corrosion properties. And CNC machining is required to achieve the dimensional and geometric tolerances of the components that are being made through additive manufacturing. So here in this slide, you can see the exclusive build of coupons that are made in different directions. This is called as Z. This is in X and this is in 45 degrees. And along with that, we have small coupons printed for evaluating the Young's modulus. We have coupons printed for evaluating the hardness, the microstructure, and also the chemical composition. And along with here, you can see along these are the three parts that have been 3D printed. Along with these parts, again, we print coupons in both Z and X directions. And once this part has been printed and subjected to post-processing, we can carry out computer tomographic inspection. And you can see here, these are components which are having very fine, intricate internal channels. So those things can be easily made out using computer tomography or digital radiography. And of course, we need to look at the microstructure in three different orientations. And also the hardness needs to be checked along with microstructure and density. And once these components have been subjected to all the qualification, we can subject the component to structural testing. So when we are talking about components for structural applications, we are testing the components to 4 times the expected loads. And also we need to carry out dimensional inspection. So you can use both computer tomography for both radiographic quality as well as inspecting the dimensions. So we also use various in situ monitoring techniques for process control. We can look at sensor-based monitoring, wherein we are monitoring the temperature, laser powers, the scan speed, and also we can use the imaging and vision-based systems for real-time imaging and analysis of printing process to detect the defects in real-time basis. And also we can analyze the quality layer upon layer by layer when each layer is being printed in that particular component. So we can collect a lot of data and we can use some data analytical tools to analyze the process data, and we can identify trends, and we can identify what are the correlations between the process parameters and the defects, which can be predictive indicators of the part quality ultimately. We can also look at robust sensor technology for real-time and accurate, reliable data acquisition. And of course, the advantages are real early detection of and prevention of defects. We can minimize scrap and rework. We can also optimize the process parameters to improve the reliability. And by all these means, we are looking at enhanced confidence in the quality and consistency of the AM components. So once a software is online melt pool monitoring, wherein we can detect the defects. So here, what we are trying to do is we are checking the volume. We are checking this. Melt pool at each and every layer. So any local variation in that energy density, we can see it can be correlated with some defects. So when this part is being built from bottom to the top, you can see here at this particular location, there were some anomalies. So based on those anomalies, you can take a call whether to continue with the printing of the component or to discontinue. If at all these levels of defects are acceptable for the end use, you can continue the 3D printing. Otherwise, you can discontinue at this stage itself so that you can save both time, effort, and also the material. So coming to benefits of simulation in additive manufacturing, we are looking at improved efficiency by optimizing process parameters. We are mitigating the risks of build failures, and we are also trying to minimize the residual stresses. So depending on the part orientation, the residual stresses can vary. And also by simulations, we are looking at achieving better surface finish and distortion control. Ultimately, we are also trying to reduce the cost by optimizing the support structures, and we are trying to print a part right for the first time. So this slide gives an example, I mean, glimpses of various parts that have been made in different alloys shown here. So I'll be talking about 2, 3 case studies on these parts and how we try to qualify them. So two such parts were made in SS316L that are shown here. So you can see here the specification for SS316L is 205 MPa yield and 515 MPa UTS with 30% elongation and 40% reduction in area. And in rod condition, we could achieve these kinds of properties. And in 3D printed condition, we could achieve properties which are well above the forged component properties. So that gives us tremendous advantage. We have again carried out a detailed qualification of these hardware. We have carried out structural testing to 4 times expected loads. And we have done detailed qualification of these parts as per AWS D20.1. And these are the first parts to fly in our launch vehicle as structural components in SSLV D1 and D2 flights. And after this, again, you can see here to make these brackets by conventional route. We were using a forging weighing almost 100 kilograms. You can see the final component weighs only 3.6 kilograms. So there's so much of material wastage involved. And also the cycle time involved is quite large. And when you do the same thing through additive manufacturing, we are able to save lot of material. And of course, it gives us advantage of increased strength. And the cycle time also has reduced to almost 1/10. Of course, the cost initially was higher, but when you adopt design for additive manufacturing for 3D printing of the same part, we could achieve cost similar to that made through conventional route. And of course, the cycle time reduction also is there. So here we are able to save 50% by design optimization through DFAM, which gives us an advantage of at least 7 to 8 kilograms payload gain in case of SSLV, because four such brackets are used in each of our flight. So this is another example of titanium alloy components that have been made through 3D printing. Here you can see these are the specified mechanical properties, and we have evaluated properties in three different directions: X, Y, Z, and 45 degrees. And all directions you can see properties are comfortably met. We have carried out detailed characterization of this, and here in case of titanium, we are definitely getting cost advantage of more than 20%. So this is another example of Inconel 718 components. So you all may be knowing it is very difficult to machine superalloys. So to achieve parts with very fine, intricate internal channels that are interconnected like this. So all these channels you can see are having dimensions of 0.9 to 2 mm. So making such part through additive manufacturing is easier compared to conventional manufacturing process. In fact, by conventional manufacturing process, it is very difficult or impossible to make such part. And here again, we have done detailed characterization. So against the specified properties, we could get very high mechanical properties. And this particular part also has been functionally tested, and it has been flown in our scramjet propulsion test flights. So this is another example of aluminum alloy bracket. So earlier this used to be made by aluminum alloy using aluminum alloy AA2014 in T652 temper condition. These are the mechanical properties specified. And we chose aluminum magnesium scandium alloy to replace this. And these are the mechanical properties that we could achieve in different directions. You can see these are well above the minimum specified properties. We also carried out additive manufacturing of very large size parts. So this is one example of a titanium alloy forged dome, which we have adopted additive manufacturing. So you can see here the input material for this making this dome used to be around 60 kilograms, and the final part weighs only 12 kilograms. So you can see this is the kind of material wastage that is there, and the cycle time used to be quite large for making such forgings. So we have adopted electron beam, wire-fed electron beam additive manufacturing to make this part. And you can see here, this is the kind of material wastage. We could minimize the material wastage from 48 kilograms to 6 kilograms, and also reduce the cycle time to less than 5 days. And you can also see here, we have achieved at least 25% cost savings by adopting additive manufacturing. So this again is one example of very large size part that has been made through additive manufacturing. So you can see here, this is the final component that we were planning to make, which weighs only 120 kilograms. And for making this component, we used to make a very large size forging, which used to weigh almost 2.5 metric ton. The forging is of this size shown here. And we used to machine out all these pockets to realize the final component. And we adopted additive manufacturing. So you can see here, we could bring down the buy to fly ratio from 21 to 3 in case of additive manufacturing. So we have also eliminated the machining operations like abrasive water jet cutting to remove these pockets. So here you need to do only parting from the base plate and milling of these faces to realize the final component. Again, you can see here all these brackets we could 3D print as a single component. So more than five parts have been 3D printed as a single component. And this is one of the largest aerospace parts in titanium alloy to be manufactured anywhere in the world. So this has been 3D printed at Shiaki, USA by wire-fed electron beam process. And we have carried out a detailed characterization of this particular component. We have evaluated the properties in four different orientations, X, Y, Z, and 45 degrees. And these are the specified properties in X and Z. And you can see here the properties are well above the minimum specified properties. And against this fracture toughness of 70 MPa root meter, we could achieve fracture toughness more than 106 MPa root meter in almost all different orientations. So again, we have identified different components that can be made through wire arc additive manufacturing process. So these are very large size components of 2.4 to 3 meter class. So these components can be made using aluminum alloy filler wire, using aluminum alloy 1201, a Russian analog of 2219. We can get a yield strength of around 350 MPa. Here, of course, being a near net shaped process, you need to have additional allowances for sufficient machining of each surface. And this is another example of cold spray additive manufacturing process. So here, unlike the previous process, there is no melting of powders involved. It's only a supersonic deposition of powders onto a substrate to make the final component. And since there is no melting involved, the residual stresses and all are minimal. Of course, you need to do post-processing in case of this particular component, like heat treatment to achieve the required strength. So we have identified different components that can be made through cold spray additive manufacturing process as shown here. And of course, one important aspect is you can make components with the buy to fly ratio as close to 1, unlike the other additive manufacturing process. So this is another example wherein you can use cold spray additive manufacturing process to make this component. So here we are using robotic cold spray process to make this component using AA2024 process. And this is one case study wherein we have used DFAM or design for additive manufacturing to optimize the mass. So this is the conventional design and we have optimized the design which is suitable for additive manufacturing. So two such brackets we have optimized, and this is where I mentioned about gaining at least 7 to 8 kilograms payload because of the weight savings we could get in these brackets. So similarly, we have optimized or redesigned the titanium alloy component as shown here. There are 24 such components in each flight. So we could redesign this component, and from 3.6 kilograms, we could bring down the mass to around 2.5 kilograms, which has directly translated into a cost savings of 80 lakhs per flight. And we also try to optimize the properties for Inconel 718 made through directed energy deposition. So herein you can see we tried out four different heat treatment cycles. These are the as-built samples. You can see here we carried out direct double aging on these in different orientations, and these are the mechanical properties. These are in as printed condition, and these are in heat treated condition. So you can see these are meeting the minimum specified properties. So this way we could optimize the heat treatment cycle for Inconel 718 by adopting a direct aging cycle. Similarly, we also tried to optimize the heat treatment cycle for aluminum 4.8 magnesium 0.3 scandium alloy. So here we saw that you can see here the data sheet specified mechanical properties of 390 MPa yield and 410 MPa UTS. But we try to optimize the heat treatment cycle further. We try to carry out heat treatment at three different temperatures, 325, 350, and 375 degrees, based on the DSC studies that we did as shown here. So based on this, we saw that by adopting a 350-degree cycle, by adopting a 375-degree aging cycle for 6 hours, we could get at least a strength which is higher than 50 MPa than that is specified in the data sheet. So by optimizing the heat treatment cycle, we are able to fine tune the mechanical properties and get very high margins even in case of aluminum alloys. So now I'll move on to adopting metal additive manufacturing at VSSC. So we first started way back in 2021 with development of passive launch vehicle components in different alloys using the powder bed fusion facilities available in the country. and we have carried out detailed characterization of these parts, and also we try to understand the process, different metal additive manufacturing process such as directed energy deposition, electron beam additive manufacturing, wire arc additive manufacturing, and also we looked at the metallurgy and NDT and post-processing aspects of it. So based on all this understanding, we are now looking at developing active launch vehicle components or even engine components. We are also looking at consolidating multiple parts and optimizing our designs. With all this understanding, we'll be further looking at developing novel designs, functionally graded materials, and also looking at new and futuristic alloys. And we'll also be able to 3D print complex systems as shown here. So our main focus has been in these aspects, design, material, process, post-processing, and also the qualification. So at VSSC, we are establishing all these facilities as shown here. We have the software which can carry out DFAM of components and also simulation of the process. We also have laser powder bed fusion machine and laser DED machine installed. And we are very shortly going to get electron beam additive manufacturing machine and also inert gas atomizer for making the powders. And also we are going to get very large size wire arc additive manufacturing machine which is capable of 5-meter class machine, 5-meter class components. So coming to DED, we can make components as large as 1.8 meter by 1.2 meter by 1 meter. And of course, these are different examples of different components that we are planning to make through directed energy deposition. So we can make functionally graded materials, multi-materials, and also we can carry out repair of components. As shown here, you can repair the components or you can add features onto an existing component. And also you can make near net shaped components with reduced material wastage. So yeah, these are again typical examples of fabrication using DED process. Repair of worn out blades, you can repair and refurbish these blades as shown here. And also you can use DED process to make bimetallic components as shown here and multi-material component as shown here. Yeah, we are trying to use electron beam additive manufacturing mainly for because it is suitable for reactive and refractory alloys. As the process is happening under high vacuum environment, it is similar to electron beam welding. So here we are looking at very large size propellant tanks in titanium alloys, and also we are looking at thrust chambers, gas bottles, and grid fins for our crew escape systems, mainly in titanium and niobium alloys as shown here. So as I mentioned, we are looking at wire arc additive manufacturing for making very large size up to 5-meter class components. So typical components are interstages, seamless rings, and propellant tanks. And also very large size brackets can be made through this route. And mainly we are looking at weldable materials like aluminum alloys, titanium alloys, and stainless steels for making these components. So one such example, classical case study is from relativity space. So they have some of the world's largest 3D printer as called as Target 3D printers, wherein they have been using both arc as well as lasers for 3D printing of the components. So you can see here, Terran 1 was the world's first 3D printed rocket, and it has flown back in 2024, and it is a fully reusable rocket. And now they are looking at making the flight in 60 days time. You can see here significantly reducing the cycle time by adopting additive manufacturing. And also you can see here the part count for the entire rocket is less than 1,000, and they are able to make the entire rocket in 2 months time. So coming to the opportunities in metal additive manufacturing for space applications, there's tremendous scope for R&D by way of collaborative projects with academia in the area of modeling, simulation, design for additive manufacturing, topology optimization, anisotropy in mechanical properties, texture, residual stresses, microstructure, and surface finish. And also we are looking at online process monitoring software as quality control tools. And there's a lot of scope for making powders and wires as feedstock for additive manufacturing. And we are also looking at AI and ML based process monitoring, inspection and quality control software. And there's tremendous scope for metal additive manufacturing startups, hubs, or center of excellence in aerospace parks, mainly for manufacture of components through additive manufacturing. And once there are more and more such places to manufacture parts, you also have the requirement of training. So there's a lot of demand for metal additive manufacturing training centers. Yeah, coming to the components that have been developed through additive manufacturing route by VSSC. So here are typical examples. So this is a very large size grid fin that we have made through electron beam additive manufacturing route. Similarly, titanium alloy dome has been made through additive manufacturing route. And these are different components that we have made in Inconel 718, aluminum alloy, and also in case of copper, we have done several nozzles for our wind tunnel applications. And we also adopted DFAM for redesigning our brackets. So there we are getting a lot of weight savings here. And yeah, these are typical components that can be more made through different metal additive manufacturing routes. We have various domes from ranging from 400 diameter to 600 and also up to 1200 diameter class. So these can be made through electron beam or wire arc additive manufacturing routes. Similarly, grid fins have already been made through electron beam additive manufacturing route. And we can have copper nozzle that is made either through cold spray additive manufacturing or DED route. And we are also looking at making very large size titanium and Inconel components through directed energy deposition routes. So again, we have a lot of bimetallic joints, be it titanium SS or SS Inconel or Inconel copper or copper SS. We have a lot of requirements for functionally graded materials for our reusable launch vehicle, which can again adopt directed energy deposition route. And also we are looking at making aluminum or titanium aluminide sandwich panels either through laser powder bed fusion or DED process. Similarly, gas bottles through DED process and also very large size aluminum components either through cold spray or additive friction stir or wire arc additive manufacturing process. So coming to the key learnings in our AIM journey, so it is again similar to computer terminology like garbage in, garbage out. So both your process parameters and feedstock need to be good to get a good product. And also we need to define the specifications very clearly without any ambiguity in development stage to reduce the cycle time for development of components through additive manufacturing. And with our vendors, we don't look at it as a vendor-customer relationship rather than as a partnership. And we are using standards as guidelines and devising our own acceptance criteria for the components that need to be inducted. And every data point that is there during our development cycle, whether good or bad, needs to be analyzed carefully. And also, we need to optimize the process parameters such as heat treatment or hot isostatic pressing. And one important learning has been there is no alternative to functional testing to gain confidence for inducting the part into our program. So NASA does extensive functional testing before inducting the components into their program. So you can see here, this is one example of a thrust chamber. So more than 11,000 seconds of hot fire tests have been done. More than 250 plus hot fire tests have been done before these components have been inducted into the program. So once during one such hot fire test, they found one failure. So here they found that this particular nozzle failed at a particular location. So here, what they have suggested is this particular failure happened because of build interruption during making the component, and during this they suggested to build full height specimens along with all components so as to characterize that particular component. So you can see this particular recommendation has been published by NASA in 2022, and we at VSSC, in fact, had a similar experience, and we published way back in 2021 itself. So during 3D printing of some component, we saw that the 45-degree specimens failed prematurely with very low elongation, although the strength was meeting the requirement. And this was attributed to incomplete melting of powder due to a build plate setting error. And our recommendation in this case was to 3D print Z specimens to the full height so that we can have enough confidence of the component that is being built. So coming to the future trends in different areas, you can see here in situ manufacturing is going to be the future wherein parts are going to be made on site both on Moon and Mars. And also we are looking at digital twins and simulation to carry out virtual testing and optimization and performance prediction. We can look at standardization and certification to adopt industry-wide standards for AM process and materials. We are again looking at sustainability and recycling, eco-friendly AM process and materials are going to be the future. We are also looking at in situ material characterization to assess properties in real-time basis. We'll also be looking at multi-physics and multi-scale modeling and simulation. We are also looking at microstructure prediction, which can predict the grain growth, phase transformation, and defects. And we are also looking at optimizing the process parameters using AI and ML-based algorithms so as to reduce the experimentation. We'll also be looking at virtual qualification and certification through simulation-based approaches rather than adopting inspection of each and every part. And also going further, we'll be looking at advanced NDT techniques for inspection of AM components. So to conclude, I can say that additive manufacturing has been a disruptive technology that has been growing exponentially worldwide and has been gaining more popularity in space sector. And there's tremendous potential for replacement of numerous conventional parts by AM by using a design for additive manufacturing in space sector, as I have shown few examples. And also I have shown examples of very critical and complex components or systems or assemblies that have been made through different additive manufacturing routes that have been already qualified and inducted into various space programs. Of course, when we started, we faced a lot of certification challenges. So this needs to be addressed to accelerate inducting AM components into our supply chain in space sector. And coming to future trends, we have seen reliable and online AI and ML based techniques for process monitoring, inspection, and quality control of AM components is going to be one important trend in future. So yeah, with this, I come to the end of my presentation, and I would like to acknowledge our management and also organizers of this faculty development program for inviting me to share my experiences. And also, I would like to thank all my colleagues as well as partners and collaborators in metal additive manufacturing and the audience for a patient hearing. Thank you. So I'm open to questions if any in the audience.
Thank you, sir, for the wonderful session.
Yeah.
Any audience, if you have any questions, you can either post in the chat box or you can ask. So there is one question in the chat box.
Yeah, bimetallic structure with
Yeah.
inconel 718 is to copper is difficult to fabricate. Yes. Yeah, it is one of the most challenging one because the alloys are different and also the alloys need to be 3D printed separately. So if you have bimetallic structure, for example, a thrust chamber, we have inner one as a copper and exterior as the inconel 718. And you need to have proper bonding of the interface when you are depositing inconel 718 over copper. And copper is a very highly conductive material, so it extracts all the heat from the inconel that is being deposited onto it. So yes, it's a real challenge. So a lot of process parameters need to be optimized. Yeah, and one more question is how can sustainability be incorporated in metal additive manufacturing parts? Yeah, see, sustainability is inbuilt when we are looking at additive manufacturing. So by adopting additive manufacturing itself, as I have shown a few case studies, we are reducing a lot of material wastage because here we are trying to build near net shaped parts. So there itself you are saving a lot of material. So that itself is an example of sustainability in the process. So by adopting additive manufacturing itself, you can say your process is sustainable because you are saving a lot of resources, especially super alloys, titanium alloys, and all are very valuable resources. So by saving a lot of material, you're looking at sustainability.
Hello, sir. Good evening.
Yeah, good evening.
Sir, this is Arun Prakash from Karungal Engineering College.
Yeah, please tell me.
Sir, is there any machine that you have developed indigenously here in India that is available in VSSC? Or you are using any abroad machine, sir, for metal additive manufacturing?
Yeah, see, it's a good question. We have not developed any machine as such because our mandate is to print parts using different technologies. So yeah, one of the machine what is there with us that is laser powder bed fusion machine. That is from an Indian manufacturer that is Amaze in Bangalore. It is from Ace Micromatic Systems. So it's an indigenously made laser.